I don't know if some of you checked, but I posted a video on the course website from the course on Monday. It might be a bit weird if you watch the video because you're going to see that it's a video from last year, and that's because I actually forgot to turn on recording on Monday. And since some people wanted to see the video, I just posted the video from last year, and it's very similar to what we did on Monday. So in case you were not here on Monday and you want to watch the class from Monday, please watch the class from last year. It's slightly different. I made some changes, but they're very cosmetic. So it should be okay. Cool. So today we're actually gonna get our hands dirty, and we're gonna start writing code. Remember, on Monday we did something which was very open and more like an introduction to the field of new interfaces for musical expression. Today we're actually going to start writing some code. Okay, so most of the programming we're going to do in 258 is going to be in the Faust programming language. To use Faust, you're going to be able to use a web interface. So it means that you don't have to install anything on your computer. You just need to go to this web page. So at this point, I all invite you to go to this web page, which is faustid.gram.fr. Okay. So there's a couple of things you need to know before you do this. If you go to this web page, you should either use Google Chrome or Firefox. Don't use Safari, don't use Edge, don't use like any other web browser. You want to use Chrome or Firefox. Why? Because if you want to do audio in real time in a web browser, it's better to do it in Chrome or Firefox. Safari is kind of okay, and Edge is really like shit, so don't even try. Another thing you should know is if you want to control with a MIDI interface the different things you're going to write here directly in the web browser, you should use Chrome because Firefox doesn't support MIDI yet. I think the most recent version of Firefox actually supports MIDI, but it's you probably don't have it. So just to be safe, you actually probably just want to use Chrome. Okay. Cool. So this is Faust. At this point, you're probably wondering why we're going to use Faust and not something else. Like I'm sure many of you already know Chuck, for example, from 220A or other classes that are taught at CCRMA. So the reason why we're using Faust and not another programming language is because Faust works very well on embedded systems. So it means that, for instance, the Teamsies, which are part of the kit that we're going to give you next week, can only be programmed in C++ or in Faust. You can't really use Chuck for that because Chuck is very nice as a programming language, and it's very convenient. But the problem of Chuck is that it's very slow. And since those computers are very small and they don't have an operating system and blah blah blah, and they don't have that much computational power, you want something which is fairly optimized. I think my microphone died, so I'm going to have to change the battery. So that's all I can hear. Sorry about this. See, like things became way more complicated after COVID. I don't know if you noticed. It's like in the old days, you just like teach. Now you have to deal with this camera, you have to deal with this camera, you have to deal with the microphone, you have to deal with Zoom, you have to not forget to press the record button, otherwise people are. Oh. Cool. So Faust is a very peculiar programming language because it's what we call a functional programming language. So who knows what a functional programming language is? Okay, not okay. So that's it's not a lot of people. So that's a very like CS concept, you know, like so. Just like for human languages, there are different kinds of languages. You know, like I mean, Chinese is very different from English, obviously. It's the same for computer programming languages, and most programming languages that people use nowadays are what we call imperative programming languages. So that's C++, that's Java, that's JavaScript is slightly functional in a way, but most of the languages that you guys know are imperative. So it means that in an imperative programming language, you start from the top of the program and you go to the bottom. It's linear, okay? So like the first thing is executed at the top, and then slowly you go down, you go down, you go down, and eventually potentially you have a loop, you know, and once the loop is over, then you keep going down, you know, like so. So there is really a linearity from top to bottom in the way the programming language, well, your program is executed. With functional programming languages, you don't have that. You can start from the bottom and go to the top. You can start from the middle and go from the top and then to the bottom. You know, like so. So it completely changes the way you approach the way you're actually going to program your computer. Okay. So all that to say that all the things that you know as a programmer, you probably have to forget them when you actually use Faust. You know. So there is no for loops, there is no while loops, there is no if statements, there is no variables, there is no functions, there is none of these things, okay? So it means that we're really starting over. So basically, if you don't have any programming background, it's actually an advantage for you compared to some of you who already know how to program a computer and who are probably going to struggle finding things that basically don't exist, okay? Anyway, so the most simple program that we can write in Faust is probably the one that we see here, and this is just a comment, okay? So if you want to write comments, it's just like in C++, you know, you do like // if you want to write comments on multiple lines, you can do /*//, okay? And so basically everything that's between this and that are being commented. So, okay, so this is ignored, and the basic program that we have here says process equals 1. So in any Faust program, there is always a process. Okay, that's like the main in C++. You need a process. That's what gives you access to the inputs and outputs of your system. By inputs and outputs, I mean audio inputs and audio outputs. Okay. So can someone guess what this program is doing? Process equals 1.
That's a DC.
Exactly. That's what we call a DC offset. So in fact, we can actually listen to it. So open up your ears, because it's not going to be very interesting. And it's going to be very short. Oh, wait. Sorry. Computer was unplugged. Okay, so okay. If you want to stop the program, you see that when I clicked on run, it opened this tab. So if I close the tab, it's going to kill the program. Okay, so that's what this does. Okay, so what do we hear here? So I know many of you don't have any background in audio signal processing, but this is what we call a DC offset, okay? So here, what we're doing is that we're sending a signal to the speakers that are in this room, and this signal is a positive signal of 1. So in audio DSP, at least in digital audio signal processing, basically, your audio signal is represented as a series of numbers, okay? That's what we call samples. And usually samples are between 1 and -1, okay? So here, what we're doing is that we're creating a signal which is just a stream of ones. Sorry. This is a signal which is just a stream of 1. So this is what we call a DC offset, okay? So from a very practical standpoint, what happens here is that when I run the program, the membrane of the speakers is being pushed forward, Okay, so you know, like a speaker, it's membrane, and the membrane has a central position. If you send it a positive current, the membrane is going to be pushed forward, and if you send it a negative current, the membrane is going to be pulled backward. Okay, so here this program is just pushing the membrane of the speaker forward. Okay, cool. So that's why when I click on run, I hear that. It's like the speaker pull, you know, going forward. And why do I hear a click when I stop the program? Why? Because it's going backward, it's going back to 0. Okay, so now what happens if I do -1? It's going backward, okay, but it's going backward from 0, okay? So it just sounds the same, okay? And if I stop the program, then it's going back to 0, okay? So I kind of lied to you because that's not exactly what's happening. Because there is this thing that we call a DC remover on a DC blocker on a computer. And basically, when you do this on your computer, actually your computer prevents DC to happen. So from a very practical standpoint, what happens here is that you're going forward, but you're actually immediately going backward again because your computer is actually automatically removing DC from the signal. Okay. What I'm saying here is not going to be very useful for 250A, but it's just like for your personal interest, you know, like if you send 1, your computer will actually remove the 1. You know, like so the click that we hear is really just the membrane of the speaker going forward and then backward again. You know, like immediately after it went forward. Cool. That's not very interesting. We want to potentially have sound. Okay, so in computer music, there is a hello world of computer music, you know, and the hello world of computer music is what? You know, it's a sine wave, okay? So here we're actually going to try to generate a sound, and that sound is just going to be a sine wave, so it's a sine wave oscillator, so we're just going to produce a signal that looks like this, okay? So how do we do this in Faust? Well, first we need to import a library, and the library we're going to import is called stdfaust.lib. Okay. And this library contains most of the standard functions that are available in the Faust libraries. And so it means that in general, in Faust, that's the only library you have to import. Cool. So here I'm going to say os.osc. Okay. Usually, if you have a sine wave oscillator, what is the default parameter of a sine wave? Well, the only parameter of a sine wave oscillator? Frequency. Okay. So here I'm going to give it a frequency for now. I'm going to say that it's 440 hertz. Okay. So now if I click on run, I hear a sine wave. Okay, so it makes sound. If I want to stop the sine wave, I click on the little cross here to close the tab, and then I don't hear sound anymore. Okay, so one thing you probably want to do is click on this little box here that says real-time compile. So basically, if you click on real-time compile, everything that you everything that you write in the Faust Web IDE will be automatically compiled into a block diagram, which actually represents the algorithm that you're trying to run. Okay, so here the block diagram that we see here is basically the implementation of the sine wave oscillator. I'm not going to go into details about this for now because it's not really interesting for 250A, but I can potentially talk a bit more about this later. Okay, cool. So we make sound. Now, we probably want to be able to control the frequency of the sine wave oscillator in real time, okay? Because currently it's static, so my program only makes one sound, and that sound is a sine wave whose frequency is 440 hertz. So a very dirty way of doing this is just to change it in real time. You can sort of do live coding in Faust. So here, if I change this to 550, okay, see, like automatically it got updated. But there is a better way of doing this. In Faust, you can actually declare user interface elements like sliders, buttons, checkboxes, or stuff like this, you know. And so here I'm going to try to control the frequency of this sine wave oscillator with a slider. To do this, I'm going to have to create a variable, which is not really a variable, but I'll tell you why I'm saying it's not really a variable. Well, you should consider it as a variable for now, okay? So I'm going to say that f is equal to 550. Okay, so now I have a variable, so-called variable, and the value of this variable is 550. You see that in Faust there is no types, so it means that there is no ints, there is no floats, there is nothing like this. You just declare a variable. In Faust, everything is a signal. So it means that even the scalar, the static value, is a signal. It's a DC offset of 550. Okay, so that's why there is no types in Faust, because basically everything is considered to be a signal. Okay, so then what I'm going to do is I'm going to replace this 550 here by f. Okay, and now if I run the program, I still get sound. And if I change the value of f, will automatically update the frequency of the sound that I'm producing. Cool. So now what I'm going to do is I'm going to replace 440 here by a slider so that I can control the value of f in real time as my program is running. So I'm going to say h slider, okay? And h slider is a horizontal slider. Here we're creating a user interface, and in this user interface there is going to be a slider, and it's going to be a horizontal slider. Means that you can also have vertical sliders if you want to. Okay. For now, we're going to stick to a horizontal slider. Okay, so that slider has a bunch of parameters that need to be configured. And the first parameter is going to be the name of the slider in the interface. And you see that we're going to use quotes to say that this is a string, okay? And here I'm going to give it a name, and I'm going to call it freak. Okay, so the name of the slider in the interface is going to be freak. Okay, there is going to be a user interface with a slider, and then it's going to say that the name of the slider is freak. Not to be confused with f, which is the variable in which the slider is connected, to which the slider is connected. Cool. Then there is going to be another parameter. The next parameter is going to be the default value. So that's basically the value of the slider when the slider starts. Okay, so when you're going to start your program, the value of the slider is going to be 440 hertz. Next value is going to be the minimum value. So I'm going to say, for example, that it's 50 hertz. So it's a very, very low frequency. The next value is going to be the highest value of the slider. So I'm going to say 2000, for example. Those values are kind of random, you know, like it could be like anything which is within the human hearing range, you know, like so anything between 20 and 20,000. 20,000 is very high, but there is one last parameter, and that one last parameter is going to be the step. So it's going to be the precision of the slider. Okay. So for example, here, if I say 1, it means that my slider is going to count 1 by 1. Okay. So you start at 440, and then the next value is going to be 441, 42, 43, 44, 45. Okay. Now, if I were to put 0.1, then I would start at 440. The next value would be 440.1, 0.2, 0.3, 0.4, etc. Okay, so this value controls the precision of the slider. Great, so now if I run the program, oh, look, I have a slider, and I can actually change the frequency of the sound that I'm producing in real time. Cool, okay. So the goal of what we're doing for now is to go towards something which kind of works like a piano, okay? So on a piano, you can control the fact that sound is on or off, okay? You can control the frequency of the sound, and you can control its volume, okay? So here so there are basically 3 parameters, right? So here we have 1 parameter. We need to add two other parameters to turn this into something that works like a piano, okay? So the next thing we're going to do is we're going to try to activate the sound or not, you know? So we want to add a button to say sound is playing, sound is not playing, okay? So to do this, I think someone has Faust stuck, no? Or maybe it's outside. Oh, yeah, we're good. Thank you. Okay, so the next thing I'm going to do is I'm going to declare a new variable, and this variable is going to be named T for trigger, okay? And I'm going to say that T for now is equal to 0. What am I going to do with T? I'm going to use T to multiply OSC to T, okay? So if I multiply OSC by T, I'm doing some math here, okay? What's going to happen?
Just be off.
Yeah, like if you multiply a number by 0, it's 0, and usually 0 means no sound, okay? Cool, and then if I do this, then it's going to be on, okay? So I want to have a button that outputs either 0 or 1, okay? 0 for off and 1 for on. So I'm going to declare a button. So those elements are standard elements of Faust, right? Like they're part of the Faust language. And button only has 1 argument, and that single argument is going to be the name of the button in the interface, and I'm going to call it gate, okay? So now if I run the program, you see that I have a button, and if I click on the button, now I can actually control the fact that sound is on or off, and I can control the frequency. Nice. So can someone guess how I'm going to control the volume of the sound now? Because if you're not too stupid, you can probably guess it. Okay, so yeah, and what would be the range of the slider? Well, let's say that 0 to 1. Yeah, 0 to 1. Cool. So here, what I want to do is to have a new variable, and this variable is going to be equal to a number between 0 and 1. Okay, 1 is going to be the maximum volume, and 0 is going to be no sound. Okay, and then I'm going to use this variable to control the gain of the sound that is produced here just by multiplying it by everything again, okay? So this is going to be my gain, and I'm going to multiply this process line by G, okay? So this is maximum volume. This is more quiet. Right? This is very quiet. Cool. So you see the point? Okay, so here we're basically dividing the overall gain of the process line by G, okay? So, do you think it would have been smarter to use a division, for example, instead of multiplying by a number smaller than 1? Well, not really. So in computer science, usually, especially if you deal with low-level stuff, divisions are not as efficient as multiplications. So usually in a computer program, you always want to make a multiplication when you can make a multiplication instead of division. Like divisions are much slower than multiplications. So usually if you divide a number by, well, if you divide a number by a number which is static, you can always replace it by multiplication, right? Anyway, so here I'm going to create a slider, and that slider is going to be called gain. I'm going to say that the default value is 0.5, the minimum value is 0, the maximum value is 1, and we have a step of 0.01. So now if I run the program, I can now control the gain of the sound that I'm producing. Cool. Okay, now I have a somewhat hard question. So do you think that this is twice as quiet as this or not? Like, do you think that multiplying by 0.5 makes the sound twice as quiet as the original version? And if I ask you the question, it probably means that there's a trap, right? So, no. Why? We hear on a logarithmic scale. So it means that if you divide a sound by 2, it's not going to sound twice as quiet. And same way, if you multiply a sound by 2, it's not going to sound twice as loud. Okay. So if you wanted a sound to sound twice as loud, by how much would you have to multiply it? 10 is a bit too much. So actually, there is no like super clean answer to this because it really depends on how you look at it. So from a purely electrical standpoint, you have to multiply it by 4. Okay, so that's the standard. But from a perceptual standpoint, you actually have to multiply it by 6. So it means that if you have, say, like one violin player, and you want this violin player to sound twice as loud, you actually need to clone this violin player 6 times. Okay, so you need 6 violin players playing together to make something sound twice as loud. Okay, so this is something you have to keep in mind. You know, like so everything that we do here with this gain multiplier is not necessarily something that's gonna control the gain in a meaningful way from a perceptual standpoint. Okay, so we'll see later how we can fix this. For now, we can just forget about it. Okay, just keep it in mind. Cool. So now we have actually something that can potentially just work like this piano. We can control the fact that sound is on or off. We can control the gain, and we can control the frequency. Cool. So if you go in the Faust web ID, and you see there is this poly voices menu here. So if you select something greater than mono or greater than 1, so say like for example 16, you're actually going to turn this Faust program into a polyphonic program. Okay. So here, by setting this value to 16, I'm basically saying that I have a polyphonic program. So you all know what polyphony is, right? Okay, so a monophonic instrument can only play one note at a time. Okay, a polyphonic instrument can play multiple notes at a time. Okay, so here we're adding the ability to the system to actually play multiple notes at a time. Okay, so so it means that potentially with this instrument we're going to be able to play chords. Okay, cool. So now that polyphony is activated, you see that here on the top right corner of the interface, there is something that says MIDI input. Here, if you select computer keyboard instead of MIDI input, you're actually going to be able to control this program with the keyboard of your computer. To do this, you want to make sure that you pressed the run button, and you kind of want to click outside of the interface so that you don't write code here that would potentially create an error. And okay, so that's very low. There we go. So now I can control my synthesizer using the keyboard of my computer, okay? And I can actually play chords. So at this point, you're probably very confused and you're like, okay, how did that happen? Like, how is the keyboard connected to this? You know, like, how does the program actually know that this is happening? Okay, so basically in Faust, and this is kind of a standard in Faust, if you declare the freq, gain, and gate parameters exactly the way I did it. So for example, if I put a capital F to freq, it's going to break everything. Okay, so like if you declare specifically those parameters, you're going to be able to turn your program into a polyphonic instrument. Okay. So basically, node on, node off. So basically, the fact that you press the button or that you're not pressing the button is going to be connected directly to gate. The velocity is going to be connected to gain, and the pitch of the notes that you are playing is going to be automatically connected to frequency. Okay, so this is kind of a Faust trick. Okay, that we're actually not going to use that much in 250A because you guys are going to make your own interfaces. So you're not going to use those super high level features of Faust, but you know, just for fun today, it's kind of cool to be able to do that kind of stuff. Do you have any questions about this or no? Yeah.
Wait, what are you typing on your keyboard? Or like to make your MIDI sound?
So that's a good question. If you press A, that's a C. So you basically want to use, you want to use the middle row of the letters on your keyboard. You know, like so, A is C, S is D. Okay, and I think the sharps are W and R maybe. So yeah, so A, W, S, E, D. Okay. If you want to switch octaves, you can use Z and X. So if it's too low, you want to press on X so that you're going one octave up. And if you're too high, you want to press Z so that you're going one octave down. Okay? Yeah?
Who might we find Faust documentation and all the...
That's a good question. That's actually a very good question. So if you go on the course website and if you go in lectures, if you go in lecture 2, in resources, there is a list of all the things that you need to learn Faust. So the Faust manual is pretty rough to read, you know, because it is a manual, you know, like so it's not very intuitive, you know, it's really just documenting every single feature of the programming language one after the other. There is a bunch of tutorials. There is documentation for the signal processing library, so like the OSC function that we're using here. And so in case you're not tired of hearing my French accent for too long during the week, you can watch the Faust Cadenza course, which is an online course on Faust that I made with Yann Orlare, who's the father of the Faust programming language. And we're both French, so you know. Anyway, so and it's kind of old now. It's from 2018, so but it should still be reasonably up to date. And it's a Stanford course on cadenza. So also, if you hover anything that you wrote, you actually get an automatic documentation here. Okay, so like if you hover H slider, see it says that the H slider primitive implements a horizontal slider, and then see label, initial value, minimum, maximum, and step. Okay. Any other question or no? So sine waves are cool, but they are kind of annoying to hear. So maybe we can use something else than a sine wave to make sound. So now we want to be able to control the timbre of the sound that we're producing. Who doesn't know what timbre is? Okay. So in music, timbre is basically the quality of your sound. Like it's what makes it's the different like harmonic content of the sound that you're producing. So a trumpet doesn't sound the same way as a piano, right? And so it's because they have different timbre. Okay. So here we're gonna try to change the timbre of the sound that we're producing, and to do this, instead of using a sine wave, we're gonna use a sawtooth wave. Okay. So to do this, I'm going to use sawtooth instead of OSC. So a sawtooth wave, so this is a sine wave, right? A sawtooth wave looks like this. It's like going down and then up and then down and then up. Okay, so it progressively goes down, and when it reaches -1, it's going to be reset to 1 immediately. Okay, so this is a sawtooth wave. So sawtooth wave have a much richer harmonic content than sine waves. So this is a sawtooth wave. Cool. So this is already slightly more interesting than the sine waves that we were using. So we're slowly getting to a point where we're going to have an instrument that actually sounds like an instrument. Cool. So one thing that I want to point out here before we continue is, so especially going back to sine waves, if I press, oops, if I, it's kind of hard. Okay, so this works, okay, but then if I have 3, okay, so why do I have this dirty sound when I have like 3 notes here? Any idea? It's clipping, right? Why is it clipping?
With each harmonic you add, it's increasing the volume.
Well, so yes and no. Sorry, I'm gonna try to get different. Okay, maybe this is better. Okay, so in audio DSP on a computer, there is a rule, and the rule is that everything that you send to your speakers has to be between 1 and -1. Okay, so like the stream of numbers, the stream of samples you're sending to the speakers, they have to be between 1 and -1. Okay, the sine wave oscillator that we're using by default is normalized, which means that it outputs a signal between 1 and -1. Okay, so what happens if you add 2 sine wave oscillators together? Well, 1 + 1 = 2. Okay, so it doesn't work. Okay, because you always want to have something between 1 and -1. So here, when I press 2 keys, it's not clicking, and it's not clicking because the default value of gain is 0.5. Okay, so because I'm multiplying the sine wave oscillator by 0.5, it means that I have 2 sine wave oscillators whose range is 0.5 to minus 0.5, which means that if I add those two sine wave oscillators together, I'm still between 1 and minus 1, okay? But if I have 3 sine wave oscillators, if I'm pressing 3 keys, then it's clipping because I'm going beyond 1 and minus 1, right? So how do I solve this problem? I can use the gain, but it's not very practical. Like, how do I make sure that whoever is going to use the synthesizer doesn't have to worry about this?
Is there a variable that you can find that's how many notes are being played currently, and then you can maybe use that to divide or something?
I could do that, but if you think about a piano, okay, so if I press 1 key, if I press 2 keys, 3 keys, okay, am I like lowering the volume of the piano as I'm pressing more keys? No, right? So it means that like the more keys you play on the piano, the louder it sounds, right? So I don't really want to adjust in real time the gain of the sound that I'm producing depending on the number of keys, you know, because from a perceptual standpoint, that's not really what happens. So no, like the only way to do this is to be like, okay, I'm making a synthesizer. My synthesizer is gonna have 3 voices of polyphony, not more, okay? So yeah, I'll say 4. So you just divide everything by 4. Like that's the only way. It's the only way. And so it means that, for example, like if you use a DAW, like a digital audio workstation, and you use audio plugins and they're polyphonic, their gain is lower than what it's supposed to be because of that. You know, because that's the only way you can do this. You know, because if you try to make something that is completely automatic, it's not going to work from a perceptual standpoint. But if you don't do this, then sound is going to click, right? So if you make a polyphonic instrument, you actually have to take that into account. You know, like, and so here I created an instrument that can play 4 notes at a time, and so I need to divide the overall gain of everything by 4 just to make sure that it's not gonna click. Okay, so those are kind of tiny detail. Oh, yeah.
So you can always only have one process, right, in a Faust program?
Yeah. But in that process, you can have multiple sounds. You know, like so. For example, say that. Okay, I'm gonna remove that for now. You know, like, but say that I want to have a sine wave and a sawtooth wave together. Well, I could just copy this and add my sawtooth wave to my sine wave. Okay, and now I have a sawtooth wave and a sine wave. Okay, so I don't hear the sine wave because it's already in the sawtooth wave, because this really doesn't make any sense, you know, like, but however, like what I could do is that I could have, for example, 2 sawtooth waves, okay, and one of the sawtooth waves could have a frequency which is slightly different from the other one, you know, like, so I could multiply f by 1.1, okay, so here I'm just like slightly shifting the frequency of the other sawtooth oscillator. There we go. Sorry. Yeah, so no, so you only have one process, but within that process, you can have as many like sound synthesizers as you want. You know, like so. Yeah. Cool. Any other questions about this, or? Cool. So I'm gonna remove the other sawtooth oscillators. So I'm gonna put things back to how they were. Cool. So how can I improve this? Okay, so now I have timbre, I have not on, not off, I have gain, I have frequency. how can I make this sound slightly more natural and a little bit less synthesized, you know, like, or make it sound more like something from the real world. This is annoying. Okay, so any.
You could change the attack and release.
Excellent. We want to add an envelope. Okay, so when you do sound synthesis, one thing that's very important to consider is the envelope of the sound that you're producing. Okay, so if you think about the envelope of a piano, it's going to look like this, right? So the envelope is basically the gain of the sound that you're producing as a function of time, okay? So when I press the key, I get like a super sharp attack, right? It's like the hammer striking the string. And then I'm gonna have a decay, which in the case of the piano is going to be exponential, right? So that's for the piano. Now, if you think about a flute, like a transverse flute, it's going to be very different, like, because it's going to take some time for the sound of the flute to start, you know, so you're going to have this. So the attack is going to be probably much, much smoother, you know, and also like sound is going to be going out all the time until you stop blowing in the flute, you know, and then eventually it's going to stop. Okay, so you see that the envelope of the sound that you're producing is very important because it really changes from a perceptual standpoint the way you hear the sound that you're producing. Okay, cool. So I'm gonna add an envelope generator, and so I'm creating this variable called envelope here, and I'm going to use a function called ASR in Faust. Okay, so one thing I didn't talk about is EN and OS here. Okay, so OS stands for oscillators. So here you're accessing the library of oscillators in Faust. And so in the oscillators library, you have a function called sawtooth. Here, I'm accessing the library where we have envelope generators, and there is a function called ASR. Okay. And that function, if I hover it, okay, here's the documentation. So it's an attack, sustain, and release function. So it means that there is an attack, a sustain, and a release. Okay, so if I were to plot the envelope that I'm going to produce here, it's going to look like this. So it's going to go up, then it's going to be static, and then it's going to go down. So this is the attack, this is the sustain, and this is the release. Okay. And I know that this might be a bit boring for some of you here, you know, like, because you've probably seen that a lot already, you know, like, but I know that there are some people who probably don't. So I think it's important that we talk quickly about this. Okay. Cool. So the different arguments of this function are the duration of the attack, the level of the sustain, and the duration of the release. Okay. So, and you can see that the durations are all in second. So here I'm going to say that I have an attack that's, for example, 0.1 seconds, so 100 millisecond. I'm going to say that the sustain gain is 1. Okay. So this is basically the value here of the gain, and this is 1. And finally, I'm going to say that release is also going to be 0.1. Okay. So you can see that there are 4 arguments. The fourth argument is a trigger signal. Okay. Well, we're lucky because we already have one from the button. Okay. So here I'm just going to plug T. Okay. So my envelope generator needs to be triggered. It needs to know when it starts. It needs to know when it stops. Okay. And the way it's going to know this is from the value of button. So if I press the button, it starts it. And if I stop pressing the button, then it stops my envelope generator. Cool. Then I need to use my envelope generator to do something here. So I'm going to replace T by envelope. Okay, I don't need T anymore because I'm using it in my ASR function. So now if I play instrument, so you can see that there's a much softer attack. It's not as sharp as before. Whoa, right? Whoa. And when I stop playing, same thing, right? There's a little decay. If I want to increase this, I can put higher values for the decay and the attack. And see. I want to break. Sorry. Just sort of. Okay, so I don't know if you heard though, but there is something weird happening now. So like if I press my 3 keys, and then if I press 3 other keys, you heard there's like a broken. Why do you think this is happening? Yeah, currently my system only has 4 voices of polyphony. But the problem is that polyphony doesn't necessarily mean a certain number of fingers playing a sound, right? If you play the piano, yes. Like if you play the piano, it's like here I have like 3 sounds. And then here I have 3 sounds, you know, like, but like the number of sounds that you hear is limited by the number of fingers that you have, right? If you have an instrument like, say, a guitar or something like this that has a long decay, then the number of sounds that you hear is not associated to the number of fingers that you have, right? So here, because I have a very long release, there is that point for 1 second where there is actually 8 sounds playing, right? Well, actually 6, right? Like, because I was pressing 3, then I pressed 3, and I still want the 3 previous sounds to play until the release is over, right? So if I want to fix this problem, probably just want to increase the number of voices of polyphony, right? Cool. So that works. Any questions about this or? Yeah.
Wait, so would you have to divide the gain by 16 here though, or?
Yes, I should, but
Okay,
I didn't do it. But yeah, very good point. Well, you know, you kind of had to find a middle ground, you know, because the problem if you divide the gain by 16 is that it's going to be very quiet, right?
yeah.
You just have to play with the instrument, you know, and as long as here, because it's a sawtooth wave, it doesn't matter too much if it's clipping because you don't really hear it that much because there are so many harmonics in a sawtooth wave that like the clipping sort of gets merged with everything else, right? But yes, I should probably like divide this by 8. You know, like, well, currently I'm only pressing 6 keys at a time, you know, like, so now it's more quiet. It depends, you know, like with sine wave, it's really extreme, like you really hear the clipping. Here with a sawtooth wave, like a bit less, you know, like, so, I mean, here we're not doing like super hardcore science in 250A, you know, like, so like, it's more like, if it sounds good, just keep it, you know, like, here, it sounds good. But yeah, that's a very good point. Cool. Well, this is really starting to look like something that actually is interesting, right? But So what else can I improve here to potentially make this slightly more interesting? So if you think of traditional musical instrument, we have one here again. So does it sound the same if I play very quiet than if I play very loud? You know, like is it exactly the same sound or not? No? Okay. So what changes in general? So usually, like the louder the sound, the more higher harmonics you're gonna have, right? So so it means that the quieter the sound, the more like the lower it's gonna sound, right? Like because you're gonna have harmonics which are lower. So how can I sort of simulate this with this instrument here? Like the fact that I'm gonna have more high harmonics when I play loud than when I play very quiet. Any thoughts? Oh. Well, maybe I can use a filter, right? And in fact, I can probably use a low pass filter. And a low pass filter is a filter that's okay. I'm gonna need the eraser now. So a low pass filter is a filter that's gonna have a frequency response that look like this, right? So it's gonna let low frequency go through and then it's gonna cut high frequencies, okay? So so it means that everything that's after this, so like this, we get rid of it. And everything that's within the zone, we keep it. And that's the frequency axis, okay? So here we're going to use a low pass filter to sort of sculpt the sound of the sawtooth wave that we are producing. How are we going to do this? So we need to connect the sawtooth oscillator to the low pass filter, right? So in Faust, you can use the connection operator to do this, which is colon, okay? So in Faust, if you say this connected to this, you're going to connect this to something else, okay? So here, I'm gonna use a function which is called resin LP. So this is a low pass filter. And this low pass filter has 3 parameters. It has a frequency, it has a Q, and it has a gain, okay? So the cutoff frequency of the filter is basically going to be this position here in the spectrum, okay? So that's where we're starting to cut frequencies, okay? So for now, I'm gonna give it a static value and I'm gonna say that, for example, this is like 5,000 hertz, okay? So my cutoff frequency is 5,000 hertz. The next parameter is the Q. Do you know what the Q of a filter controls? Yeah.
Is it like this?
Exactly. So basically, the higher the Q, the sharper the slope, or like the steeper the slope, okay? So if I have a very low Q, then my filter is gonna look like this, okay? If I have a very high Q, then my filter is gonna look like this, okay? So now, what is a high Q and what is a low Q? So usually a Q cannot be lower than 1, okay? So the 1 is the lowest Q you can have. And then I would say like the highest Q is maybe 50 or 60. It's not very precise actually, you know, like because beyond a certain point, it's just going to sound the same basically, you know. So you can have a Q of 1,000 if you want, but the difference in terms of how it sounds between 1,000 and 40 is not going to be that big, but it's going to be very big between say like 1 and 10, for example. Okay. So for now, I'm going to set a Q of 7. And the last value is just the gain of the filter, so I'm going to set it to 1. Okay. So you can see now that the block diagram of the program that we're writing is a little bit more explicit than what we had before, right? So we have a sawtooth oscillator. The sawtooth oscillator is multiplied to an envelope generator, okay, which is our envelope generator. It's also multiplied to G, which is a slider, okay? So you see, it makes sense, right? And finally, the output of this last multiplication is connected to the low pass filter, okay, which is what we have here. And that's the sound that we hear. Does that make sense? Or cool. So how does this sound like now? So you see that it actually sounds quite different, right? There is this like I don't know if you hear it well. Okay, so just to highlight the E a bit more, I'm going to increase the Q. Okay. You hear like this. Okay, so why do I hear this? Does anyone know? Yeah.
As in reality, increasing the view is a, will create a little bump at the top of the list.
Yeah. So there are many, many different kinds of low pass filters. It turns out that the one that we're using here is a resonant low pass filter. So it means that the frequency response of this filter is not exactly the one I lied again, sorry. And so it's not exactly this, it's more like something like this. So there is a little bump before the cut, okay? So draw this like properly. So there is a little bump before we actually start the cut, you know? And so this little bump that we have here is a resonance, okay? The higher the Q, the sharper the resonance is going to be. You know, like so if you have a Q which is very high, then the frequency response is going to look like this. Okay. So, but then if you have a Q that's very low, then the resonance is probably just going to look like this. Okay. So the Q has an impact on the steepness of the slope of the filter, but it also has an impact on the sharpness of the resonance, okay? So this is why here, as I increase the Q, I increase the resonance. And so basically the sound that we hear, like this like super high-pitched sound that you hear in the background, that's basically the resonance, which currently is at 5,000 hertz. So the super high-pitched sound that we hear is just a 5,000 hertz sine wave, okay? If I were to decrease this value here, then it would, see? Now it's lower, okay? Cool, so, yeah?
Are there filters where the Q doesn't have as big of an impact on the
Yes, absolutely, but they're boring. So, no, but actually, so let me comment this out here. So in Faust, there is also a low pass function. This one doesn't have resonance. Okay, so this one is completely flat. The thing is, with this kind of filters, which are called Butterworth filters, it's much more complex to control the slope of the filter, okay? So if you look at the documentation for a low pass, you see that it only has two parameters. It has a filter order and it has a cutoff frequency. So the cutoff frequency has exactly the same effect as the resonant low pass filter, but the filter order here has basically allows you to control the slope of the filter, but it has to be an integer. And so you have way less control than with the resonant low-pass filter on the slope with this kind of filter. Okay, so but we can try to see what it does, and you'll see why I say that it's more boring. Okay, so I'm going to say, for example, the order is going to be 6. Okay, so that's way more standard, you know, in the sense that this really acts as what you think it would do, you know, like, but the resonance you'll see later, like when we actually start playing a bit more with the filter, it really adds this sort of very natural thing to the sound that you're producing, you know, like, and the regular low pass filter doesn't really have that. You can, I mean, you can use it if you want, you know, like it's like maybe you prefer it, you know, like it's just that I personally prefer resonant low pass filters. That's it's very subjective. Okay. So the higher the order of the filter, the steeper the slope. Okay, so if I put a very high order to my filter, then it's very, very steep. One thing you have to keep in mind though with this kind of filters is that the higher the order, the more computation it involves, okay? Which is not the case with the resonant low-pass filter. Like the resonant low-pass filter has a fixed memory and computational like footprints, okay? The low-pass filter, like the Butterworth low-pass filter, where you can control the order of the filter, doesn't have a fixed footprint, doesn't have fixed footprints. So if you increase the value of the order, it means that it's going to imply more computation. And so currently I'm running everything on a computer, and my computer is pretty powerful, you know, like, so I don't really care about like how much computation this is going to take. But in 250A, we're going to use the teensies, which are very, 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 very tiny computers that are not very powerful. And so you actually have to take those things into consideration when you're actually working on your algorithm. You know, and so optimization matters in 250A way more than in probably any other class that you took potentially at CCRMA. So any other question or? Yeah.
Now that you said this, if there's any way to check how much computation is using?
Yeah, I guess just go in your terminal. And,
But I mean in the Faust. Well, I know how to do that.
there we go. So it's very hard to know with Google Chrome because it has like so many processes. Like, well, in Faust, no. Like, well, but you know, like the thing with Faust is that Faust is it's not like Chuck where there's like a virtual machine, you know, and that kind of stuff where you know exactly what the virtual machine takes in terms of computation. Faust is a programming language, like, which is compiled. So it means that currently Faust is running in this web browser, but Faust could be running on like your smartphone. It could be running on an embedded system. It's like Faust generates C++, basically, you know. So it means that here we could potentially add a feature to the Faust web ID that tells you how much the Faust web ID takes in terms of computation. But it's not really Faust itself, you know, because Faust itself is just something that generates C++ code or WebAssembly or whatever you want, you know, like so there is no virtual machine in Faust like you have in Chuck where you can know exactly how much computation the system is taking, right? So what I'm saying is like it's a little bit like if you were trying to see how much your C++ handwritten program was taking in terms of computation. You know, like it's not so much your C++ program, it's more like the environment in which your program is running. I don't know if that makes sense. But.
It makes sense, but how do I know? In the manual of documentation, do we have this filter uses more computation than this one?
Oh, that's a good. Not really, no. Like, but then it's more like a DSP question, you know, because like if you know signal processing, you know that a Butterworth like I would say like this is almost like common sense in a way, you know, like for like if you know DSP, you know, like but it's true that maybe that's something that should be put in the documentation of Faust, you know, like but especially if you're using Faust at a very high level as we're doing it in 258. But like, you know that from an architectural standpoint, a Butterworth filter is going to be way more expensive than a biquad filter like the one used for the resonant low pass filter. So the answer is yes or no. Like just. Any other question or? Okay, so it's nice to have a filter. Okay, I'm gonna put back the regular resonant low pass filter as we had before. Okay, so it's nice to have a filter, but what I wanted is to have a filter whose parameters are changing in real time in function of the sound that I'm producing. Okay. So here we have an envelope generator. The envelope generator tells us what the shape of the envelope of the sound that we're producing is. So what I want to do is I want to use envelope to potentially control the cutoff frequency of my filter. Okay, so that if sound is loud, the cutoff frequency is going to be higher than if sound is quiet. Okay, so it means that now I'm going to have a dynamic spectrum to the sound that I'm producing. Okay, so how do I do this? Well, it's pretty straightforward. So I could just use envelope here instead of the static value for my cutoff frequency. The problem is that what envelope outputs here is a number between 0 and 1. Okay. So I want to turn that into a number which is closer to what a frequency is. Okay. So for example, I could say that I want to produce a frequency which is say like 1000 at the minimum. Okay. But okay, I'm gonna say like 500. Okay. And then I can say that the maximum is going to be like, okay, so if I multiply this by 5000, for example, okay. Okay, so now I'm producing a number between 500 and 5500. Does that make sense? Okay. So why is it better? Well, you see now I have dynamic spectrum. Okay, so like when I start playing the notes, so you hear the resonance now, like because the resonance is sort of going across the spectrum of the sound that I'm producing. It's going up, so it's a right. So that's the resonance. So see now it's clipping, and that's because I'm not dividing everything by 3 when I'm playing it on 3. Okay, so this is very basic sound design principle, like just the ability to sculpt the sound in real time as you're producing sound. You know, like, and this is something that you can very easily do just with an envelope generator and a filter. So here I could do the same thing with the low pass as you suggested, and I could say, for example, okay, so this is my cutoff frequency. I had to put the order, so that the order here is 5, and then I have an extra parameter, 2 extra parameters, okay? So So you see, you don't have like the wow, you know, and so that's why I was saying that Butterworth low-pass filters are slightly more boring than resonant low-pass filters because they don't have the resonance, you know. But then it depends, you know, like this sounds more and more like Queen, actually, right? Like just cool. So the main advantage of Faust in that context is that you don't really have to think too much about plugging things to things because there are no types, you know, like, so that's why you can just take the envelope and multiply it by 5,000 and use that to control the cutoff frequency, you know, like with other programming languages, you would have to think about the types and if things are running at a certain speed or whatever. Here, you can really just plug everything to anything. And the Faust compiler is smart enough to make the right optimization so that there is not going to be any problem in your program. So, do you have any questions about this or? No? Yeah.
You mentioned earlier that these are not real variables.
That's a good question. So, so basically, like, say that I'm trying to create a variable, okay, and well, say that like t is a variable, okay, and you consider that t is a variable, okay. But then what is envelope? You know, like envelope here is more like a function, you know, and it could be a function with an argument, and that argument could be, for example, the attack, okay, and then I could pass attack here as an argument, and then I could control the duration of the attack here, same way as I did it before. Okay, what did I break? Oh yeah, two envelopes. Okay, cool. So what I'm saying is that from a semantic standpoint, it's not super clear like what the difference is between this and this, you know, like, so in Faust, you're building a block diagram, and you're building a block diagram of a signal tree, basically. So the only things that you do with those things, they're more like tags in a way to a signal generator, okay? Button is a signal generator. It generates a signal which is either a 0 or 1. Okay, and so the tag to button is t, and so t is just a name for that signal generator in a way. Like so that's why I'm saying that they're not really variables and they're not really functions per se. Because from a semantical standpoint, they're, you know, like it's very different from what you would have with an imperative programming language. So just to sort of bounce back on what you just said, I'm going to show you that there is a bunch of things that you're probably going to struggle with a lot with Faust. So for example, say that you assume that t is a variable, okay? So if it's a variable, you would be like, okay, maybe I can change the value of t later. You know, I can say that t, for example, is now equal to 0. Well, this doesn't work because t is not a variable. And so from the Faust standpoint, doing this is not like changing the value of a variable. It's actually doing this thing that we call pattern matching. And I'm not going to explain what pattern matching is now because like we don't really have time for this. Like maybe later into 50A, like well, like it's not going to help you to make better musical instruments. But all that to say that you're probably going to struggle with that kind of problems, you know, because you're going to be like, okay, yeah, I'm going to try to redefine t, but you can't redefine t. And that's a feature of functional programming languages, because in a functional programming language, you can put anything anywhere. And because you can put anything anywhere, there is no continuity in your program, okay? And if you were to write something like this, you would sort of consider that first this is executed and then this is executed. But it's not the case, you know, like, and And so in Faust, you could totally put the process line before everything else, and it would not change anything. So that's a valid Faust program. There is no continuity in your program because it's a functional programming language. Okay. Any other questions? No? Okay. So I think that that's like an operational synthesizer at this point. You know, like there is not that much that we can improve to it for now. You know, well, I mean, we could improve a lot of things. You know, like and probably make it sound better. But from a sound design standpoint, it has all the features that you expect from a synthesizer. You know, so I'm gonna show you something which is like slightly different now. And to show you this, I'm gonna kind of start over from just a empty process line. This is all on the course website. So like if you were completely lost today, this is all like documented and written, you know, there is a tutorial, you know, like so in fact, I can show you this just now. So if you go on the course website, if you go in labs assignments, you see that there is lab 1. Faust basics and digital musical instruments. So everything that we've done this morning is documented here, okay? So if you were completely lost, I strongly recommend you to have a look at this because this is definitely gonna be very useful. Well, in any case, you should probably have a look at it, okay? Cool. So I want to start showing you things that are a little bit more advanced in Faust, okay? And just to sort of try to give you a slightly more intuitive understanding of what we're doing here. So the first thing I'm going to do is I'm going to set this back to 0 because, well, actually to mono because well, depending on what you do, you don't necessarily want to have a polyphonic instrument. And so in many cases, it's just simpler to just have mono. This can create a lot of problems sometimes. So just we'll leave mono. Okay. Cool. So this is a valid Faust program. And here we're using the underscore operator. And the underscore operator in Faust is a pass-through, okay? So it's basically something that describes a signal, but that's just an empty signal with nothing in it, okay? So here, what my program is doing is that it's taking an input and it's passing it to the output. So from a practical standpoint, what do you think would happen if I run this program, well, or if you run it on your computer? Well, it's going to do something. It's actually going to make sound, probably. What happens if I connect the input to the output? What is the input? What is the default input on your computer, like, usually? Well, you can select it in the settings of your computer, but like the default audio input on your computer. Yeah, that's like the microphone, right? Okay, so this is the microphone, and here I'm connecting the microphone to the speaker. What happens if I connect the microphone to a speaker? Feedback, right? Okay, so if I run this program, I'm gonna get feedback, okay? Because again, this underscore here specifies an empty signal, you know, and so it's just a signal passing by. It's a pass-through, and so this pass-through is connecting the input to the output. Okay, I'm not going to do it because, yeah. Well, you can try. Yeah, one thing that I just want to tell you, like, especially if that's the first time that you take a class at CCRMA and you've never done things like this before. So you're probably going to work with headphones, right? which is a good thing. You know, like you definitely want to work with headphones. You have to be very, very careful when you write your own audio processing and you use headphones, because this can potentially be unstable. And if it's unstable, what's going to happen? It's going to make a very loud sound, right? And if you're wearing headphones, it's going to be very painful. So there is no safeguards here, okay? Like you're the master. So usually, especially when you're going to work with the teensies, like the teensies, there is even less safeguards than on your computer. So all that to say that usually when you work on audio DSP and you write your own algorithms, like the process is, first you run the program, you don't wear the headphones, and if it doesn't make a horrible sound and it seems safe, then you wear the headphones, you know, like, but you don't always wear the headphones, because if you do that, then you're really taking risks, okay? So keep that in mind, okay? Cool, so in Faust, you can take a signal, but you can also split it. So this operator here is the split, sorry. This operator is the split operator. So it takes an input signal and it splits the signal into a certain number of signals, okay? So the colon operator here is just a way to put two signals in parallel, okay? So if I remove the beginning of the statement here, then I have two signals in parallel. That's what the colon operator is doing. So if I add another underscore like this, then I have three signals in parallel, okay? Four signals in parallel, okay? So if I do underscore and then split, then I take an input signal and I split it into two signals, which are now like two parallel signals. Okay? So you can put anything you want in parallel, you know, like so you can have something like this, but you could potentially add like a 1 in parallel of everything. Okay, so now I have an input signal, split it into two signals, and just a signal generator which outputs 1 all the time. Okay. Cool. So if there is a split operator, there is probably a merge operator, right? And so the merge operator is just the opposite, okay? So here we're taking an input signal, we're splitting it into two signals, and then we're merging those two signals back again. Okay, now I have a question. Do you think that this is a passive operation? And by this I mean, like, do we have the same thing here in the input than here for the output? Like, say if I send 1 here, do I get 1 here or something else? Yeah. You get 2. Yes. So that's one of the dirty things about, well, I don't know if it's dirty, but like it's one of the things about Faust. So here, if you split one signal into two signals, you're creating two copies of the signal. And then if you merge those two copies again, it's like if you're adding them, okay? So it means that if you had 1 here, then it means that now you have 1 here and here, okay? So like 1, 1, 1. And so because you merge those two ones together, that makes a 2, okay? So basically this thing that I just wrote is a multiplier by 2, okay? If I wanted to have a multiplier by 3, I could just do this, okay? So now I'm multiplying this input signal by 3, okay? So if I put 1 here, then I get 3 here. Yeah. Yeah.
What does that mean to multiply it by 3? Like how it would sound?
if you multiply it by 3, it means that it's going to sound louder. Like if you like put an input signal in here and you do this, then it's just going to sound like 3 times louder. Like what we're doing right now is completely useless. Just so you know, like it's only done so that you understand the way the programming language actually works. You know, like, but in practice, you're never going to have to write something like this in Faust. You know, like it's just that I'm trying to show you like how those different operators function basically. And so actually we can try, you know, like, so if you run the program, okay, it's not making any sound. And that's because you can actually select what the audio input to your program is going to be. So you can choose the built-in analog input of your computer, which is probably going to be the microphone. But you can also select an audio file. And so this is the audio file here that is connected to your Faust program. So if I play the audio file, so that's the audio file here going through this Faust program and then being sent to the speakers. Okay. If I, you know, remove this and just do it like that, see, it's more quiet. You know, so so the audio file here is very convenient, you know, because if you need to test things out, it's very convenient to have this audio file that you can just send in your Faust program whenever you need to. So cool. So by the way, so you remember this is the basic pass through. You see that if I play, oops. Run the program, if I play the program, I only get sound here, right? Do you hear that? There's no sound on the speaker. There is no sound on the speaker because the program that I wrote only has one output, okay? Now, if I use the split again, and I run the program, then I have sound on the other speaker. Does that make sense? So if you want to have a program that uses the 2 speakers, like especially if you use headphones, it's going to be really annoying. Like if you use headphones and your program only has one output, it's only going to go on one side. Okay. So if you want to have sound on both sides, then you want to have 2 outputs to your program. Okay, so for the time left, we're going to do a little exercise just to see if you kind of understood what we're doing. So I would like you to start from this and implement a panner. So what is a panner? A panner is a program that will allow you to control the amount of sound that goes to the left or to the right, okay? So basically, we're going to have a slider, okay? If the slider is at the middle, then you get the same amount of sound on the left and on the right, okay? If the slider is all the way to the left, then you only hear sound on the left. And if the slider is all the way to the right, then you only hear sound on the right, okay? And the input to your panner is going to be this audio file, okay? So you need to create a slider, and then you need to see how you can interface your slider with this program so that you can control the amount of sound you get on the left, the amount of sound you get on the right. Does that make sense, or? Okay, just to give you a little hint to get started with this. So the algorithm for this is going to look like that. So you're going to have an input. Okay, so that's your audio input here. Okay, we can call it X of n. Okay, and then we're going to split this input into 2 signals. Okay, one which is going to go to the left, one which is going to go to the right. Okay, So that's already what we have. Then we're gonna have two multipliers. So in audio DSP, well, or just in DSP in general, like when you have this little triangle in your block diagram, it means that it's a multiplication, okay? So it means that you're multiplying the input here by some number, okay? Then you're gonna have the slider, okay? The slider is going to output a certain number, and then you're gonna have to interface that number with this multiplier and with this multiplier, okay? And obviously, what's going to happen here, it's not going to be the same thing as here, right? Like, because otherwise it would sound the same on both sides, you know? Like you want to basically counterbalance what you do on one side while it's happening on the other side, okay? So I would like you to spend maybe like 5 minutes trying to do this, you know, and then we can look at a potential solution, and then we'll talk about this week's assignment. There's going to be an assignment this week. So. How do I, what, sorry? So the first thing is you want to make sure that polyphony is not active, okay? So currently, yeah. Okay, so if you press play button, I think audio is probably off on your computer. No, yeah. Oh, so yeah, so if you wanted to replace this by an oscillator, you could just replace the underscore here by the oscillator. So. Did you succeed or that? Okay.
Difference with the default ones, manuals you can
So sometimes, just want to. Yeah. So one thing you should know. One of your colleagues found out about this. Like so. We're manipulating a lot of memory related things in the web browser, and the web browser doesn't like that too much. So sometimes it's possible that your program doesn't make any sound, even though you think it should make sound. So that's the case. Like if you have a doubt and you're like, oh, it really doesn't make any sound, like it should make sound, just refresh the page. Okay. Refresh. Okay, and you see that it's supposed to keep it. Like you're not gonna. Well, okay. Just to be safe, maybe you want to copy and paste what you have here somewhere on your computer. Like so that you don't lose everything. Like just in case. Like in theory, it's not supposed to happen. But between theory and practice, there is always like some differences. Like so. So you want to make sure that you save what you're doing, then you refresh the page, and after that it should work. Okay. So here's a potential solution. So I'm going to create a pan function. Okay. So I'm going to say that pan is equal to what I had here. Okay, and I'm going to activate real time compile. No such file or directory. Okay. What did I do? Okay, well, I guess. Okay. Cool. So I have pan. Pan is equal to this. Okay, and I'm calling pan in process. And so I'm trying to make things in a clean way. I'm trying to encapsulate things in an actual function. Okay. Cool. So I'm going to create a slider, and this slider is going to be called P, and P is going to be my panning here. I will say that the default is 0.5, the minimum is 0, the maximum is 1, and we have a step of 0.01. Okay. So basically, this is left. This is right. Okay, so what I want is that when P is equal to 0, because it's on the left, then I hear sound on the left. Okay, so I'm just going to multiply this by 1 minus P. Okay, and then I'm going to multiply this by P. Okay, does that make sense? Or so if I run the program, now I only have sound on one side. I'm going through the room. I have sound on the other side. Okay. Cool. So that was pretty straightforward. Okay, just one last thing. So do you think that's a good pattern, or do you think that's a bad one? Bad. Okay. Why is it bad? Exactly, because again, when you control the gain of something, it's on a logarithmic scale, right? So it means that here, as I'm moving sound in space, there's kind of a weird gap in the middle because gain is not expressed on a linear scale. Okay. So there is a trick to fix this in a very quick way, and it's just to take the square root of P, okay? And so if I take the square root of P, like at least from a perceptual standpoint, there is a slightly cleaner way of doing this, but this is kind of the easy, simple way of doing it. If you take the square root of the slider, then it's actually going to be sort of accurate from a perceptual standpoint. So if I run the program again, now the gain should be somewhat equal across the entire thing. And you see that here, what I did is that I took slider and I connected it to square root using a Faust connector, like the connection operator. I could have done this in a more like imperative way, just so you know, like, so that you're not like completely lost. I could have just said like square root of slider. That's the same, okay? So doing this or doing that are completely equivalent. So it's just that this is more like a block diagram way of doing things, like, and so from a Faust standpoint, it kind of makes a little bit more sense. So cool, okay. So do you have any questions about this or no? Okay. So for this week, or like for the rest of the week, I strongly encourage you to read the lab, okay, and to do it, even though the lab is very similar to what we've done in class. Like if there are a couple of things you didn't really get or whatever, you should probably read it. And then scrolling down, you see that there is an assignment 0. Discovering and playing around with Faust. It's due on April 12th, but it's not really due on April 12th because, in fact, because this is assignment 0, you don't have anything to actually give us. Okay, so it's more like for you. Okay, so it's not going to be graded or whatever. Like it's just like a little warm up. Okay, so review all the steps of lab 1 and make sure that you understand them. Okay, we're in 250A we do so many things. There is like, so we're only going to spend like 2 weeks on audio processing and Faust, and then we're going to do something completely different. So so all that to say that like if there are stuff you didn't get here, it's probably the right time to figure them out. Okay, so by doing so, try to make some basic modifications to the example codes to solidify their understanding. Peruse the content of demos.lib, physmodels.lib, and the Faust example page. Try to run the Faust 250A starter codes. Okay, so basically just read this and you do it. Okay, and then you should be good for the rest of the week. So next week on Monday we'll give you the kits. Okay, so it's gonna be a little box. You're gonna take it home. Just well, if you have a bike, or it's not like huge or whatever. It's probably gonna fit in your backpack. But you probably want to have like some rooms in your backpack. Okay, just so you know. Cool. Well, thank you. Have a good rest of the week, and if you have questions, you can shoot us emails. Thank you.